All right, so what were we talking about last time?
We were drawing pictures.
We were drawing pictures, yeah. And we drew some pictures of the wave functions of that particle in a ring. And we were showing its maximum, minimum. And what happened as we increased values of ML is ML increased by 1 or decreased by 1. What happened to the number of nodes?
We increased by 2.
Yep. Okay. We did the mathematics to show that that was true. Okay, but let's talk about some degeneracy in this system. Because if you remember, we wrote like plus or minus, and those had the same values. So let's show that there is, in fact, degeneracy in this system. So do you remember what degeneracy meant again?
Orbitals with the same energy levels.
Yep. Orbitals of same energy. Oh, yep, energy. But what was different about them? Different. What do we have?
Different orbital types, so like P versus X, or P versus like.
No, not that.
Just the quantum numbers.
Yep, they have different quantum numbers and therefore different wave functions. Okay. So let's determine the energy for a particle on a ring. For ML is equal to 1 and ML is equal to minus 1. Okay, do you remember what the energy expression was for a particle on a ring? Or what quantum number is important here?
ML squared H bar squared over 2I.
Yep. And what was I again?
That was MR squared, and that's
Yep.
what is that? I forget what it's actually called.
Yep, mr squared, where m is the mass of our particle, right? And r is the radius at which it's traveling. This is the moment of inertia. Yeah. Okay, so now let's calculate when energy of ML is equal to 1 and when it's equal to -1. So what's the value going to be for this system? Where we have ML is equal to 1.
H bar squared divided by m 2 mr squared.
Yep. What about this guy? Same thing, right? Thanks to that square root symbol, a lot of these are the same, so we get the same result. Thanks to that ML squared part. So therefore, values that are not 0 are doubly degenerate. What we're going to do, we're going to plot these. We'll have energy on this axis, and what we're going to plot is that energy level. So what is the lowest energy level we can have in this system?
0.
Yep. ML is equal to 0. Drew a really big line there. Now, what's the next lowest in energy?
ML1
Yep,
or -1.
yep. Okay. Now, what about the next one? And one question, so we know what the value of the next one's going to be. What's it going to be?
Or -2.
2 and
Oh.
-2.
Yeah, 2 and -2. But now the question we want to ask is what about that spacing? Oops.
It's going to be squared spacing. So
Right. So note, it's not going to be the same, like this delta E here. Let's say from 1 to 0. If we draw another one, we're going to have M sub L. The spacing is going to grow much bigger, 2, -2. And if we're looking at this energy, 2, 1, that the energy of 2, 1 is greater than that of delta E 1, 0. So the spacing is going to increase as we increase that ML value, right? And John, you're exactly right. We have those squared values. That square in the denominator makes a big deal, while the square up top also makes it. Okay? Everyone feel comfortable with that? Okay. So now what we're going to do is we've gone to rotations in 2D. Let's move on to rotations in 3 dimensions. Am I okay to move this up?
Can I have 1 second?
Sure. So this next system is called the rigid rotor. And we're going to talk about what does that look like, but actually we'll wait for the rigid rotor. Let's do rotations in 3D. So everything's moving around on a 3-dimensional surface. Okay. So the next section was called rotations in 3D. And I think that's what the title of the section in your book is called. Okay, so we're going to consider, again, we have a particle with mass m. That is free to move in any direction on a sphere. And that has a radius of r. The potential on that surface is equal to 0. And it's infinite everywhere else, we'll say. Okay, so let's try to draw our system. Circle. Shoot. There we go.
Damn circles.
I know, they're too hard. So that's
You're going for
the
the actual circle or the inside circle?
this actual circle. That's
Okay,
I feel
okay.
like the inside circle wasn't too bad, but this one, man, that's botched. But that's our sphere. We're trying to draw this in 3 dimensions. We have a couple things we need to keep track of. What are the dimensions we need to keep track of?
Radius?
Yep, radius. So we got some distance from the center out. Call that r. What else do we have?
X and Y.
When you say we want to go into spherical polar coordinates right now.
Theta.
Yep, theta. And theta, which one's theta?
Great question. No idea.
I think it's the bottom one.
Theta. So theta, I think, what is it?
Oh, I'm doing it.
Theta phi.
Mm.
So I think this one, this angle right
P is
here
X and Y.
is phi, and this one marks theta. Does that make sense? Or can you guys see that, or do I need to zoom in a little closer? Ah, hey, there we go. So this one, the angle that's going this way, I think it, like in the horizontal plane, is phi. Let's see if that's true. Oops, that's not connected. Images. Yep, that's right. Sorry, got overly excited about that. Okay. So now we have this fictitious system. Where do we always start when we go to model a new system?
The Schrodinger equation.
Yep. So we're going to go to the Schrodinger equation. The first thing we're going to do too, we have to get that Schrodinger equation. So we have to know, what does the Hamiltonian look like? So Schrodinger equation, someone spout it off for me.
H
One.
H hat.
times wavelength equals E times wavelength.
Wave function, right?
Wave function. Whoops.
Yep, there you go. I know one of my friends who works at Intel, he has this actually tattooed on his foot.
Guys, we need to step up.
Let's,
We need to step it up. We're all getting matching tattoos.
all right, let's go. That's what we'll do with our YouTube money, right?
Yeah, I was gonna say I don't have matching tattoo kind of money right now, but you know,
We
I
might.
know a guy that'll do it for like $15 total.
yeah, you're probably right. Okay. Yeah. Probably knows about it.
Oh, it's disgusting.
That's
That's,
great.
that's is it. I used to have a friend. He would do them himself. He would like poke himself with a needle and then just go
Oh.
in.
I've
They were
seen people do that.
terrible.
No, this
I'll learn on the fly if I have to. If we're being
Don's face.
is the guy my friends go to. He lives in like Olean. It's like his side job, but he only charges like, I think like $20 a tattoo.
See, I feel like you want to pay a lot of money for a tattoo.
So
Okay, so let's look at that Hamiltonian. Okay, what do you think? The Hamiltonian's always broken down into what parts?
Kinetic and potential energy.
Yep, kinetic and potential. Can we simplify this in any way, shape, or form?
potential is 0.
Yep, this one's 0, so it drops out. We set that up, or our problem up that way, so that guy is 0. So we're just left over with the kinetic energy operator. And what do we generally use for the kinetic energy operator?
H bar squared over 2, negative H bar squared over 2m.
Yep, negative H bar squared, whoops, over 2m.
D
And what else?
squared dx squared.
Yep. So, but how many dimensions do we have here?
We got 3, so d squared dy plus d squared dy squared plus d squared dz squared.
Yep. Okay. Or we can represent this in a different way. Do you remember how we can represent this this differential, this added differential?
Simplify it down to its principal quantum number.
Not quite yet. Do you guys remember this symbol, or do you remember seeing it at all?
You did mention
Girl.
that.
Yeah, we mentioned it maybe once. Sometimes you see it in like multivariable calculus, sometimes in Calc 3. So know that these two things are equivalent. Okay, but there's going to be a problem here where we have too many variables and we can't separate them. So we're going to have to go to spherical polar coordinates. So recall, which doesn't look like it's any easier, but I promise you it is. Recall that delta squared, that was in spherical polar coordinates, it was equal to 1 over r, differential of r squared dr plus 1 over r squared sine squared theta d phi, second derivative of that guy, plus 1 over r squared sine theta d theta sine theta, oops, d theta. Oh man, that looks pretty brutal. Can we simplify this in any way based upon our system? Do we know if anything's constant?
So R.
Yep, r is constant. So since r is constant,
When would R not be constant, I guess?
in actual atoms, r is not
Mhm.
constant.
Okay.
So we're gonna get there, but we need to talk about some other things first. All right, since r is constant, what can be simplified in this expression? Is there anything that's going to drop out?
The whole first term,
Yep, the whole first term. Why does the whole first term drop out?
it's all R. There's no change in R.
Well,
Yep,
the
so-
derivative is always going to be constant, 0.
Yep, derivative of the constant 0, so that's 0. So then this delta, or this gradient, excuse me, is equal to just the second term. So r squared sine, oh, I'm sorry, I wrote a sine squared in there for some reason. That shouldn't be there.
Oh.
I don't know why I did that. Sine theta phi squared plus 1 over r squared sine theta d theta sine theta d theta. Right? Okay.
Seems reasonable.
So now, then what's our Hamiltonian going to look like?
H bar squared negative over 2m times that.
Yep, and is there anything we can pull out of here?
The 1r squared sine theta.
We can pull out this r squared. We're going to leave the sine theta in there. The reason for that is theta is going to change. And since that changes, these differentials get messed around. Like, see how there's this order here?
Mhm.
That order actually matters. So we can't, conventionally you think we could pull that out, but what you learn from linear algebra is you can't like that. So we're going to leave those ones in, but you're totally right about that r squared. So we're going to pull that guy out, and we're
10
left over with
30. I'm totally right.
technically correct, the best kind of correct, right?
Yeah. I like that these are recorded. Whenever I'm feeling low, I could just go back.
Maddie's secretly half of your views, is what she's trying to tell
Yeah.
you.
Yeah. Yeah, we got to get wackier or whatever. I don't know.
I
What does
surround myself
Paul,
with the iPads.
what's Paul Logan do? He like, I don't know, just
Oh,
irritates the hell
sounds
out
like
of everybody. We got to wait for bombers to come in. I guess apparently people have been doing Zoom sessions and like there are people who sneak into them and like do like pranks and stuff.
Oh my
Yeah,
god.
I've seen that.
I've seen those too. They're so bad.
They are. That's pretty funny though.
Someone has to invite them though, so that means that it's got one of us has to be the link.
I'll do it. I don't care.
Actually, when I first started working at Penn State Barron, a student would run in like a morph suit to people's classes randomly. And he came into mine and like I was like, yeah, we made it. That's awesome. Didn't really know what to do. It was a good day. We've seen this a couple hundred times before. What's this lower part here?
2i.
Yep. So we can leave that in there. Now, this becomes extremely taxing to write out over and over and over again. So what we're going to do, we're going to label this whole thing with that symbol. It's a Greek letter that I can't remember right now. What is it? Oh, keep typing on a thing that isn't typing. Left, upside down. I love how I can Google that. That's great. Okay. Oh, this is lambda. Sure.
That's a capital lambda.
That's a capital lambda. Yeah. I should have known that. You ever watch Revenge of the Nerds? Lambda, lambda, lambda. That movie's terrible. It's funny though. Okay. So now if we, yeah. It's like Animal House. You think it's like it's like, oh man, this is a good college movie. It's like one of the worst college movies ever. Super. However, I want Dave Hilmy to just yell or Animal House at me once. All right, so we have, oops, we don't need that M in there. We need an I. Get rid of that guy. Should be equal to this. Right? Now, in the past, when we've tried to solve these equations, what have we done?
Made assumptions.
Yeah, we make a bunch of assumptions and try and solve it that way. Yeah. Before we do, we've already made a lot of our assumptions, so we're good there. How do we deal with equations like this? And remember, this is like a second derivative here. Or what do you know from differential equations? How do you want to manipulate this to make this easy to solve?
Solve for psi first.
Yeah, we need to find something for psi. What we want to do is we want to get this second derivative term, this guy, we want to isolate it by itself. Because then we can come up with equations or ideas that should make this work out. So how are we going to manipulate this around? What is this lambda squared psi? What's that going to be equal to?
Negative 2i over h bar squared, or negative 2ie over h bar squared times psi.
Right. So we're going to try and solve this differential equation. Okay, we're going to make this a little bit simpler too. This thing here, what could we do to it? Or is anything really going to change in here? Like once we know our system. Oh,
Constant.
yeah, we're just gonna have a constant. We're gonna call it little epsilon for now, even though we use that a million times for other things. Physical chemists aren't creative.
It's all the same letters.
You guys should just start making up variables or symbols, and then you'll really fucking credit out there.
Well, we could get a little more musical.
Draw a scale of the Mona Lisa.
There's that one. Isn't that like
Too many dots. Maddie doesn't like that stuff either.
Yeah, no dots. What is there? We could do, what is it, like a coda? That's a coda, right?
That works.
I'm trying to think of all the music symbols I learned back in high school, but can't remember any of them now.
A lot of it was just like fancy F's and P's to just
Yeah.
to say like fast and slow. That's all they do.
But yeah,
For
and for
Monty.
forte,
Pianissimo,
and all that stuff.
Fortissimo.
So you do pay attention in Italian. It's not all just uno.
Or Josh is telling us he was a nerd in high school too.
I played the trumpet for like 3 or 4 years.
Aw,
That's what it was. I played it until middle school. That's why I know.
Have one in your house?
how cute.
I do have one in my house. Yeah,
Pull it out now.
it would take me a minute.
Play us something.
Yeah, play us
Oh
a
god, you don't want to hear that. I quit when I had braces because like whenever I would play the trumpet, it would cut my gums open.
Oh.
Like I would have stuff to cover my braces, but it would still hurt so bad.
Art is pain.
That's-
Art is pain, right?
That
How much
that-
was I willing to sacrifice? Not that much.
what about you guys? Did anyone else play any other instruments?
I was in the bell
I played
choir.
many instruments, not good at any of them. Like played piano, saxophone, guitar. Not really great at any of them.
You go, John.
Mr. Musician over there.
Allegheny's finest.
Oh yeah.
Oh yeah.
I always wanted to play the accordion really bad. I don't know
Or
why.
I heard
Maybe
it's
it's just from Weird Al.
I could see you pulling one out of like a bar.
Didn't Evanovsky Cole play the bagpipes?
Yeah, she played the bagpipes, and she was really good at them, actually.
Those
Yeah.
are
I could hear it when she would crank them out. I could hear them from my house. She lived on like the top of my hill, and about a mile and a half away.
I would call the police.
They're that loud, though.
I love the chemistry student on this YouTube page, like stressed out, like in a rush to like learn, and we're just talking about this now.
Yeah.
That's what they got to learn. Relax. It's just pecan, man.
If they made it this far, they can relax. Yeah.
So we have this psi, but what does psi depend on? So what are the variables it depends on?
Theta and the other one.
Theta and phi.
Phi.
Yep, that's right. Okay, if these two are separable, so meaning we can pull them apart, we can actually get two functions out. We can say that psi is a combination of a term that just depends on theta and a term that just depends on phi. So we're going to try to draw a capital theta, which, I don't know, looks like a chubby kid. I don't know. That's what I see. Or a frog.
Looks like
We'll
an
draw a frog in a
H
minute.
circle around it. Oh.
Chubby kid.
Yeah, I see a chubby kid, like, just like,
Yeah.
Oh,
that's his
yeah, I
mouth.
see what you're saying.
Oh, now I see it.
We don't have to draw these are his eyes. These are chubby kid.
Aw.
And that's kind of, so we did the 3D sonogram of my daughter. She kind of looks like that. And then we have a term, phi, that's by itself. So we can say these two are split up. Okay,
So what is that chubby kid term supposed to be?
that's meant to be a capital theta.
Capital theta. Okay.
And this is a capital phi. So we have to verify this. So if we want to verify this, we have to plug it into the Schrodinger equation and show that it's true. So to verify this, that's psi is separable. Man, I'm having a tough time spelling today. We're going to plug into the Schrodinger equation. And we said if we take the differential of this, what's this equal to? Or like this was h hat psi, and then what else do we have over here?
Negative h bar squared over 2I.
Yeah.
And
we
downward.
simplified that, right?
No, wait, no, negative 2IE over h bar. But then you give that a symbol? Is that right? You give that epsilon, so epsilon pi?
Yeah. We're going to
Epsilon
say negative epsilon. Because actually back here, I shouldn't have boxed in that negative value. We're going to leave that negative out. And there's a reason for that. It'll make more sense when we start looking at this. So we get this. Just like Josh said. Okay. Now we got to plug this in with our two functions. We got big theta. It depends on small theta. Capital phi. It depends on little phi. If we start plugging those things in, we have 1 over sine theta. There is a squared in this. I screwed up back there. I'm sorry. There should be a squared back here.
back where?
Sorry about that. So it should be a sine squared here.
Okay.
We got d phi squared. Both of our terms, we're going to leave off what it depends on for a minute. Plus 1 over sine theta d theta sine theta d theta capital theta phi. And that's all equal to negative e which I don't have enough room for, phi b. Okay. Can we simplify this? Or looking at these differentials, does this differential apply to both of these functions? What does theta depend on again?
Sine phi. No, theta or phi?
This capital theta, what does it depend on? Or what's in the brackets here?
Theta.
Yeah, theta. So this depends on that a differential with respect to little theta. This one depends on a differential respect to little phi. So looking at this term here, can we simplify that? Is there anything we can pull out in that term?
Is that just going to go to 0 or something, or 1?
So 1 over sine theta can be taken out, right?
We're going to leave that here for now. This guy, right along in here. If we take the different, like let's say, for example, we have a function that is equal to xy. Oops, except it's not on the page. You don't have to write this down. Let's say we do this. What's the result going to be?
That's just X.
Yeah.
It would just be y.
Or wait, no, just Y. Oops.
Y, yep. Because what we're saying is this, right?
Mm-hmm.
Right. So let's say we have we've got that guy. What's that going to work out to be?
The I thing times partial of h circle over h circle squared.
Yep. Oops, I picked the wrong one. That guy. Like that, right?
Yeah.
Because this one depends on theta. What does this one depend on?
Both?
Phi.
Or is it phi?
Being with
Just
phi.
phi.
Okay.
Okay. So what we're going to do is we're going to use that type of knowledge where this function right here, this one only depends on theta, and this guy right here, what does it depend on?
Phi.
Right. So any spot that we have a differential, all we have to do is look at it and say, all right, what are we differentiating with respect to? And then we can pull out other terms. Okay? So let's do that. So this term, what's going to happen with it? Do you guys, are you guys writing that down, or do you want me to, can I cover this up?
1 sec.
Okay. We'll get our next slide ready. A lot going on there.
Looks like hieroglyphics to me right now.
Sorry, I'm sure my handwriting helps out a ton too.
All right, go for it.
Okay, so let's start breaking this guy apart. So this first term, what's it going to look like? Keeping in mind, we're differentiating with respect to phi. So we're going to have the sine squared theta on the bottom, right? That doesn't change. What's going to happen with this? Can we pull anything out of there? Or what are we differentiating with respect to?
Phi.
Phi, yep. And which of these functions depends on phi? The first one or the second one?
Second.
Second one.
So, oops. We have that guy. And what happens to this?
It comes out.
Yeah, it comes out just like our y in this function. It was just treated as a constant. So we're just going to pull it out. We're going to have that theta term. Okay. Now we got to look at this term. In the end, we have this differential, right? Is there anything we can pull out from here? What does that first term depend on?
Theta.
Theta. So what does this term depend on? Phi, yep. And we're differentiating with respect to theta. So what can we do with this differential?
remove the phi.
Remove the I.
Yep, we can pull that I out. We can throw that right out front. So we get sine theta, d theta, sine theta, d theta, capital theta.
Why don't we do that for both of the d thetas?
So why don't we do it for both of these? Because
Yeah.
remember, when it comes to operators, we have to, in differentials, you operate always to the right first. So we're going to do a differential, then we're going to multiply it by sine theta, then we have another differential we have to do. So really, this looks kind of like, that would be a little more mathematically formal. Does that make sense, Ellie?
Yeah, that makes more sense.
And all of this is equal to negative E times capital theta, capital phi. Okay. So now we need to try and separate these guys out. In order to do that, we've done this for a particle trapped in a 3D box. What did we do for a particle trapped in a 3D box? Or how could we just get one term on a side? We want to basically isolate this E by itself. What would you do?
Divide by everything.
Yep, so we want to divide by these guys, right? So divide by I and theta. When we do that, let's write that in. Sine squared theta, theta I. This is going to stay the same.
So wait, the H, are we not crossing out terms yet? Oh, okay.
Yep, not yet. You can if you want to do it while you work along. So that's what we get. And John's real eager. What do you want to cancel out, John?
I believe in that first term, it's going to be that H things can cancel.
Yep. What about in this guy?
Yeah.
I's.
Yeah. Those are gone. So we're left over with this.
So why is that sine theta not being divided by HI? That's part of the second term.
Can you repeat your question again? I'm sorry.
So that second sine theta, the one that's d, so sine theta d8.
That one.
So why is that not being divided by
Because remember, the order when you differentiate matters. So we can't just pull that one out yet.
I got you.
Yeah. Because we don't know, it doesn't necessarily mean it commutes if it differentiates, which is a weird idea to think about because in most mathematics that we deal with, they all, like, stuff always commutes. But like we learned way back near the beginning, sometimes functions don't commute when you differentiate. Does that make sense?
Yeah.
All right, so we get this in the end. 1 over sine squared theta I. I'll just call it I for now. Now I'll call it phi. I'll go back. Capital phi plus 1 over sine theta capital theta. Sine theta differential with respect to theta capital theta. Equal to negative E. Okay. Any other things you could, whoa. We're moving slow. Thinking of any other things that we could get rid of in this, or we could divide by.
No. Nope.
A lot
Multiply by
everyone,
sine.
yeah, we want to get rid of this thing actually. Because we have a second derivative here. We want to isolate that guy by itself because it'll make solving this problem way easier. We're going to get rid of that one. So we're going to divide by sine theta, sine squared theta. Okay. We do that, that first term's going to go away. We're left over.
Did you mean multiply by sine squared theta?
Yes, I do mean multiply. Whoops. So multiply this whole thing by sine squared. That first term goes away, right? Because we're going to have sine squared up top, so we're left over with 1 over capital phi. This guy. And then sine theta over capital theta. Theta, sine theta, theta, capital theta. And that's all equal to what if we're multiplying by sine squared?
Negative epsilon sine squared theta.
Yep. Okay. We're going to rearrange this so we can solve this in an easier way. Whenever we want to solve an equation, what do we always make one side equal to?
0.
Yep, 0. So we're going to move this over and make that 0. So rearrange.
Do you think I first?
Yes.
Rearrange, and then we get 1 over capital theta e phi plus sine theta over capital theta differential with respect to theta, sine theta, that guy plus e sine squared theta. That's all equal to
Her
0.
Wi-Fi crashed and she got kicked out of Zoom.
Oh, we got kicked out of Zoom?
Ellie.
Oh, oops, I
It'll be like that.
lost her. Does she need another invite?
No, because I think she would just go to physics right now.
Oh, okay.
No.
Yeah. Yeah, we're running out of time, but one last thing I want to say. What was the benefit of doing this?
You separated terms.
Yep, we did. This. What's that only depend on?
I.
Sine.
Yep,
Phi.
phi. And all of this stuff, what does that only depend on?
Theta.
Circle.
Yep.
That kid.
This one we've done already. That was with the particle on a ring. Now we got to worry about this guy. So next time, that's what we're going to do. We're going to look at solving this differential equation. Okay? All right. A lot of mathematics thrown around this time and a lot of symbols. Are there any questions?